Imagine your sentence is a little group chat, and every word could tap another word and ask, "Hey, how much do you belong here?" What if all those whispers could rewrite the sentence together? That's self-attention, no magic, just math. Let's say you're teaching a robot to read words. It starts with a simple rule. Every word means the same thing every time. But life isn't simple. The word bark can mean a dog's sound or the outside of a tree. How does the robot know which one to pick? Old tricks like fixed rules fail. We need something smarter. Here's the trick. Every word packs its meaning into a tiny list of numbers. We call this list a vector. Think of it as a tiny box with numbers inside, like a suitcase with only 3 pockets. For cat, let's use 1, 2, 3. Now let's pack dog. 2, 4, 6. Notice something? Dog is exactly twice cat. The numbers are proportional. That's a clue these 2 words are related. Here's the cool part. To see how much 2 words belong together, we multiply their numbers in pairs and add up the results. That's called a dot product. For cat and dog, 1 times 2 plus 2 times 4 plus 3 times 6 is equal to 2 plus 8 plus 18 is equal to 28. Big score means they're close friends. Now let's add a third word, Matt, with vector 1, 5, 2. Let's ask how much cat belongs with Matt. Dot product time. 1 times 1 plus 2 times 5 plus 3 times 2 is equal to 1 plus 10 plus 6 is equal to 17. Lower score means cat and Matt are more like distant cousins. So far we've done one-on-one chats. But self-attention lets every word ask every other word at the same time. We stack all these dot products into a little table. Rows are the asking words, columns are the answering words. For 3 words, it's a 3 by 3 table. Watch this. Cat asks cat and gets 14. Cat asks dog and gets 28. Cat asks Matt and gets 17. Each number is how strongly cat feels about each word. Same for dog and Matt. Now we have a little map of who likes whom. But these raw numbers are too big. If we use them directly, dog would always win because it's twice as big. We need to shrink them so they add up to 1. That's what softmax does. It turns scores into probabilities. Let's softmax the first row, cat's row. First, we raise e to each power. E to the power of 14 is almost equal to 1.2 times 10 to the power of 6. E to the power of 28 is almost equal to 1.4 times 10 to the power of 12. E to the power of 17 is almost equal to 2.4 times 10 to the power of 7. Sum them. About 1.4 times 10 to the power of 12. Now divide each by the sum. 0.000001, 0.999998, 0.00001. Cat mostly listens to dog. Same trick for dog's row. E to the power of 28 is almost equal to 1.4 times 10 to the power of 12. E to the power of 56 is almost equal to 2.8 times 10 to the power of 24. E to the power of 34 is almost equal to 6.5 times 10 to the power of 14. Sum is almost equal to 2.8 times 10 to the power of 24. Divide. Dog mostly listens to itself and cat, almost not to Matt. So dog's weights are 0.50, 0.50, 0.00. And for Matt's row, e to the power of 17 is almost equal to 2.4 times 10 to the power of 7. E to the power of 34 is almost equal to 6.5 times 10 to the power of 14. E to the power of 30 is almost equal to 1.1 times 10 to the power of 13. Sum is almost equal to 1.1 times 10 to the power of 13. Divide. Matt mostly listens to itself. So Matt's weights are 0.00, 0.02, 0.98. Now stack the softmax rows back into the 3 by 3 table. These are our attention weights. Each word now has a tiny probability list telling it who to listen to most. Cat, 0% cat, 100% dog, 0% Matt. Dog, 50% cat, 50% dog, 0% Matt. Matt, 0% cat, 2% dog, 98% Matt. Here's the magic. We take each original vector and mix it using these weights. For cat's new vector, We take 0% of cat, 100% of dog, 0% of mat. So cat's new vector is just dog's original vector. 2, 4, 6. Dog's new vector, 50% cat plus 50% dog, so 1.5, 3, for 0.5. It's a blend of cat and dog, like a cat-dog hybrid. Mat's new vector, 2% dog plus 98% mat, so 1.04, 5.1, 2.04. Almost the same as mat, with a tiny sprinkle of dog. Now each word has a new vector that carries context from the whole sentence. Before, cat was just 1, 2, 3. Now it's 2, 4, 6. It knows it's sitting on a mat with a dog nearby. That solves our bark problem. The model can look at the whole sentence to pick the right meaning. Let's zoom out. The whole self-attention step is just 3 tiny matrix multiplications. First, we pack words into 3 matrices. Q, questions, K, keys, and V, values. Then we compute QK, divide by the square root of the vector length, softmax, and finally multiply by V. That's it. In our tiny example, Q, K, and V were all the same matrix because we're just starting out. But in real models, each word asks 3 different questions, looks at 3 different keys, and packs 3 different values. Still the same math inside. Let's run the numbers for the full 3 by 3 case. Q is our word vectors, K is the same, V is the same. Compute QK. That's our raw attention table we made earlier. Divide each number by square root 3 is almost equal to 1.73. Then softmax each row. Finally multiply softmax by V. Same result as before. You just watched self-attention in action. Words talk to each other using tiny number lists and a few matrix multiplications. No black boxes, just clear math. And it's not just theory. Every big language model uses exactly this trick to understand sentences. But here's the catch. What if the sentence is long? Say 100 words. The QK matrix becomes 100 by 100. That's 10,000 dot products. For 1,000 words, it's 1,000,000 dot products. That's a lot of math for the computer to do. That's why real models use tricks to save time and memory. One trick is called sparse attention. Only let each word ask a few nearby words, not all of them. It's like giving each word a tiny local chat instead of inviting the whole class. Another trick is to shrink the numbers using fewer digits. Instead of precise 32-bit floats, we use 8-bit integers. That's like switching from a fancy camera to a quick snapshot, faster to compute, still good enough for the big picture. And sometimes we split the sentence into chunks and process them separately. It's like reading a book in pages instead of one long scroll. Each page gets its own quick self-attention party. So self-attention is powerful but hungry. It scales with the square of the sentence length, so long sentences slow it down. That's why engineers keep inventing clever shortcuts. The math stays the same, we just make it faster. Let's peek under the hood with a real code snippet. Here's what the attention step looks like in Python using PyTorch. We define 3 matrices Q, K, V, then one line does the magic. Attention equals softmax. Q at k.t/authority d_k at V. One line, 3 matrices, and the sentence is rewritten. Notice the tiny change. We divide by the square root of the vector length, square root d_k. That keeps the scores from blowing up when vectors are long. It's like leveling the playing field so no word can shout too loud just because it's big. Let's see the payoff. Before self-attention, the model didn't know bark could mean 2 things. After self-attention, the vector for bark carries context from the whole sentence. The model now sees the sentence is about a dog, so it picks the animal meaning. No extra rules, just math. Self-attention is clever, but not free. It needs memory for those big matrices and time for all those multiplications. For short sentences, it's a superhero. For novels, it needs helpers like sparse attention or 8-bit math. The core idea stays. Let words peek at each other using tiny numbers. Self-attention is just smart word gossip done with numbers. If this clicked for you, Hit subscribe and watch the full video to see how these tiny boxes power tools like me. That's all for now. Thanks for peeking into the math.